Welcome back to Einstein Mechanics. Today we are going to solve some complex and application questions under this chapter. This is the second set of problems. You can check out for the first set in the chapter 5 or episode 5. So let's get started. Here we are going to apply certain knowledge. The sliding plate viscometer shown below is used to measure the viscosity of a fluid. So its function is used to measure the viscosity of a fluid. The top plate is moving to the right with a constant velocity. So this is the velocity of 10 meters per second in response to a force of 3 Newton. The bottom plate is stationary. What is the velocity of the fluid or the viscosity of the fluid? Assume a linear viscosity distribution. Are we good? So we have this problem given. We are to determine what? Viscosity. Assume a linear viscosity or a linear velocity distribution. So what is the formula? Or let's first list down our parameters given in this question. Are we good? So from the question, this sliding plate viscometer is used to measure what? Viscosity. Are we good? So its function is used to measure viscosity. And we are given some parameters. Looking from the diagram and from the viscometer, we have some dimensions given, some length and some what? Width. So can I say the length is given as what? 100 mm, which is the same as what? We convert it to meters. Are we good? Which is the same as 0.1 meters. We also have the width given. Pay attention. This I have to take my time and go through. We have 50 millimeters, which is going to give me 0.05 meters. And from the question 2, we have a constant velocity of 10 meters per second. So velocity here, I will represent it by what? U, not mu, U. So velocity is given as 10 meters per second with a force of 3 Newton. So we have a force which is what? 3 Newtons. Are we good? So looking at the diagram, there is a certain space, a 1 millimeter space between the top plate and the down plate, which is the distance between what? The plate. And in fluid mechanics under this chapter, distances from the walls are given by what? Y, which is equal to that. So our distance between the plate, Y, distance. So the distance given is given as what? 1 millimeter. And we know how to convert it to what? 0.01 meters. Are we good? So with this written, the question is asking us to what? What is the viscosity of the fluid? And we know the formula of what? Viscosity and shear related. We know that shear stress is given as mu, which is the viscosity, and we know du on what? Dy. Are we good? So from this formula, we can calculate for the viscosity. So can we say that the viscosity mu is given as the shear stress on du dy? Are we good? All right. So from here, we can find our shear stress from these parameters. Is that true? We know that shear stress from mechanics is given as what? The force over the area. The force over the area. And looking at the viscometer, there's a force of what? 3 Newton acting upon it. And we can calculate the area of what? The viscometer, which is the length times what? The width. So can I say my shear stress is given as the force, which is my 3 Newton on the area. So the area will be 0.1, which is the length, and the width 0.05. And this is giving me for the shear as 600 Newton per meter square for the shear. Are we good? So since I have the shear now, I can move forward to calculate for what? The viscosity. I know the formula. Now I have my shear. Do I know the du dy? Du means change in what? U, or dy, which is change in what? The distance. But looking at this question and the parameters given, are we having any change in u? So we will take our du as what? The u, which is the velocity, and our dy, which is the same as the y, as the distance between what? The plates. So we can say that from here, our du is giving us u, which is 10 meter per what? Second. And our dy, which is the same as what? The y, is also giving us 1, which is 0.001 meters. I'm working everything in meters, so you should also work everything in what? Meters. I can now input my values and say that this viscometer is measuring a viscosity of, the shear is 600 on my du, which is 10, on dy, which is 0.001, and this is giving me a viscosity of 0.06. We know the unit for viscosity, Newton second per what? Meter square. Or this is 6 to the power negative 2 Newton second per meter square. Are we good? So this viscometer with the parameters given is measuring a 0.06 Newton second per meter square viscosity for the fluid it is in. Are we good? So this is the approach you have to. We already know the formula for what? The shear relating to the viscosity when there is what? A linear velocity between them. Are we good? We already established this in the episodes. And we know viscosity is equal to shear on du dy. We know the formula for shear, force over area. We have our force. The area can be calculated. So the area, a fluid takes the area of the container. So we can get the area from the container. And we have it. We know that our du, which is the velocity, is given dy, which is the distance between the plate, is also given. Then straight away, we are getting our viscosity. So these are some application questions. Let's move to the next question. The velocity distribution for water, pay attention here, for water at 20 degrees Celsius near a wall is given by this formula. So the velocity distribution, the u, is given by a formula where we have our a to be that, our b to be that, and y is the distance from the wall. As we saw in the first example, y is the distance between the plate or from the wall in millimeters. Determine the shear stress in the water at y equal to 1 millimeter. So now the y is 1 millimeters. And let's write down our parameters. So here we have the velocity distribution. The velocity distribution, which is given, so the velocity is u, and it is given by this formula. Pay attention to the formula: a y on b, all raised to the power 1 on 6. So this is the velocity, and we have our a to be 10 meter per second. The b is also given us 2 millimeters, and that can be converted to meters, which is 0.002 meters. We have our y, which is also given as 1 millimeter, which is also 0.001 meter. We have all our parameters written, and we are to calculate the shear stress. The shear stress at this distance. Do we know the formula for the shear stress? Yes, we know that our shear stress is giving us our viscosity du on dy. Are we good? Do we have our viscosity from the question? No, but we can get our viscosity. How? It is obtained from tables that at 40 or at 20, the temperature is 20. At 20 degrees Celsius of water, you'll be given a table. So questions like this, you have to get the table. At 20 degrees Celsius of water, the viscosity, which is mu, is a constant value, which is 1.00 times 10 raised to the power negative 3 Newton seconds per meter square. So this is obtained from what? Tables. It is already calculated for. So we now have our viscosity as a constant at this temperature of water. We now need our du on what? Dy, but we have the u. So how do I get my du on what? Dy? Calculus, right? So I have to differentiate u with respect to what? Y, and that can be done. So now du with respect to y, differentiating this u with respect to y is the same as, I'm just doing the differentiation. You can check out for the playlist, there is differentiation inside, you check it out. There we go. So this is the same thing as, I'm just rewriting this again. This is the same thing as a on b 1 raised to the power 6 multiplying this y 1 to the power 6. So this is what I'm going to what? Differentiate. And when I differentiate this, I am going to get a on my b 1 on 6 multiplying 1 on 6 y. You subtract 1 from this, which is going to give me negative 5 on what? 6. So my better expression of du dy is going to be a on, I can bring my 6, 1 on 6 multiplying this y negative 5 on 6. So this is the differential of what? The u. And I want to get the value. I already have the value of the viscosity. Can I get the value of this by putting in a, putting in b, and putting in y? Yes, I can get it. So my du dy is very simple. From the question, I got my a to be 10. Then this is this 6 multiplying the b, and b here is 0. What? 0.002 raised to the power 1 on 6. Raised to the power 1 on 6 multiplying this y, which is 0.001 to the power negative 5 on 6. And when you punch this on your calculator, your du with respect to y should give you a constant value, which is 1485. The unit is per second. Are we good? Look at this. This is u, which is, the unit is velocity, meter per what? Second. Are we good? Per second. And this is also what? Y, distance, divided by meter. So the same thing here, meter per second. This can be times 1 on meter. They will cancel themselves and it will be per second. That's why we are getting per second for the units. So now I have a constant viscosity here. We are to determine the shear. I also know the value of the strain, which is the u on the y. So straight away, my shear for this is giving us, what is the value? Which is 1.00 times 10 raised to the power negative 3 multiplying the strain, which is 1485. And my shear stress is giving us 1.49 Newton per meter square, or Pascal. Are we good? So this is how we go through it. When you're given the u, which is the velocity in an equation form, to get your strain, which is the u on the y, you have to differentiate the velocity with respect to the y, and you are good to go. Let's look at a more complex one, which is very interesting, and we are going to love it. So we have this question over here. An interesting one, of course. So we go through it. This question has a lot. It says, suppose that glycerin is flowing at a temperature of what? 20 degrees Celsius. And that the pressure gradient, dP on the what? The X is negative 1.6 kilonewton per meter cube. What are the velocity and shear stress at a distance of 12 millimeter from the wall if the space between the walls is 5 centimeter? Again, what are the shear stress and velocity at the wall? The velocity distribution for the viscous flow between the stationary plate is given as this. This is an interesting question. You don't need to panic. First, write down your parameters and check out your table for the constants you will need. So what fluid is this? This is a glycerin. So flowing at what? 20 degrees. So can I say at 20 degrees Celsius of this fluid, from my tables, I will check what is the viscosity for that. Then, because looking through the formula, there's a viscosity what? Given. Mu is given as what? We have to find it out. It's given us 1.41 Newton second per meter square. This is read from tables. For this fluid flowing at this temperature, its viscosity from tables is 1.41 Newton per watt second. Are we good? And this is the velocity distribution. Our U is given in an equation form. So I know that my U is given as negative 1 on 2 this mu multiplying the P on what? Dx. And I have by minus y squared as my what? Velocity. Pay attention. And I'm giving this dP on dx as negative 1.6 kilonewton. So I have a value given. DP on what? Dx is negative. Remember, it is kilonewton. So can I say it's the same as negative 1,600 Newton per meter cube? Yes, it is given. Are we okay? What is the velocity and the shear stress at a distance 12 mm? So we are given a certain distance, which is our y from the wall is 12 millimeters. So 12 mm. And can I convert that to meters? Yes, which is 0.012 meters. What again do we need? We've gotten all our parameters. But remember, this question is in twofold. First, it says what are the velocity and shear stress at a distance of 12 millimeter from the wall, if the space is that. And again, what are the shear stress and the velocity at the wall? Two different questions. First, the velocity at a distance of 12 millimeters. Second, the velocity and shear at the wall. But at the wall, there's a y given, which you should know off head. We will talk about that. So first condition, the velocity and the shear at 12 mm. How do we go by that? Remember, this U represent the velocity because the question says the velocity distribution for the viscous flow between the stationary plate is given as this. So they've already given us the velocity and they're asking us the value of what? The viscosity. Here we go. So at the A part, we are to find the velocity. Let's see. So the velocity at this 12 mm distance, we can just find it by inputting the values in it, and we'll get an answer for the velocity. Here we go. So the velocity will be my u. This is not mu, it is u, velocity. Negative 1 on 2. What is the value for the mu? It is given as 1.1 or 1.41 multiplying this dp on ds, which is given as negative 1,000 600 multiplying a B. What is our B? Which is giving us 5 centimeters. So our B is giving us 5 centimeters. Converting it to meters, we are going to get 0.05 meters. So that will be 0.05 multiplying from the equation y. Y is that 0.012 minus y squared, which is 0.012 square. Then you close your bracket. So when you punch everything here, you are to get your velocity at 0.261. Remember, velocity is meter per second. Here we go. So with the parameters given at 12 millimeter from the wall, the velocity is given as 0.261 meter per second. Here we go. So can we find the shear, because it is asked what is the velocity and shear, and we know that our shear is giving us mu du on what? Dy, but we already have our mu since it's we know the fluid involved and we know the temperature. We read it from tables. We know our mu given, but do we know du dy? No. So we have to differentiate this u with respect to what? The y, then input the values again to get the du dy. That's quite interesting. So let's do the du dy here. So I'm going to differentiate this with respect to y. So du with respect to y is going to be, we assume this, all these are constant because they do not involve what? The y. So check out for your differentiation very well. So we just differentiate this and that. And our du with respect to what? The y is going to be this form. -1/2 mu multiplying this dp on dx. Then multiplying, if you differentiate this, you are going to get the b. Minus, if you differentiate this, you are getting your 2y. So this is the derivative of what? The u. And since we want the value for du with respect to what? The y, we can input the values and get that. So here, my du dy is going to be still -1/2. And the mu is known, 1.41, multiplying, this is -1600, multiplying our b, which is 0.05. 0.05 minus 2 times our y, which is 0.012. And here, my du dy is giving me, when you punch everything here in du dy, you're going to get 14.75. And remember, we saw that the unit for du dy is what? Per second. So here, the shear, I'm looking for the shear. I know the value of mu. I now know the value of what? Du dy. And so now my shear is going to be now viscosity, which is 1.41 multiplying du dy, 14.75. And this shear is going to be 20.8 Newton per meter square, or what? Pascal. Are we good? All right. So the shear stress acting on the fluid at this distance 12 millimeter is giving us 20.8 Pascal or Newton per meter square. The derivative is found, and let's tackle the second aspect. So the second aspect is like, what are the shear stress again and the velocity at the wall? At the wall, what does that mean? So let's look at what this means. At the wall, we want to find out what at the wall means. Are we good? Okay, so a new page. What we have to know is that at the wall, our y is equal to what? 0. Y is equal to 0 at the wall. So you go through every process we went through again where your y is what? 0. So we were asked to find for what? The u. First, this is the formula for the u. It's giving us negative 1 on 2 mu times our dp dx multiplying our what? What's the formula? Again, you can record the formula, which is by minus y squared. Are we good? All right, so now let's find the velocity at the wall where y is 0. So our velocity is going to be 1 on negative 1 on 2. This is 1.41 multiplying negative 1600 multiplying b, which is 0.05 multiplying at the wall y is 0 minus this 0 square. And remember, 0 times any number will be 0, and all they are in terms of what? Multiplication. So which will render the u to be 0.00 meter per second. What does this mean? This means that at the wall, there's no what? Movement of the molecule. That's what we call no slip condition. Remember, no slip condition. So at the wall, those particles attached to the wall are stationary. That's why we are getting the velocity of 0.00. There we go. So now the shear at the wall, what happens? So no movement at the wall. What about the shear? Let's see. So we also know that still our shear is mu du on what? Dy. Are we good? Mu du on dy. But we've already known the derivative of what? Du dy. But we saw that our du dy is giving us, we saw the formula. Du dy is giving us negative 1 on 2 mu multiplying our dp dx multiplying our b minus 2y. So here, since we are at the wall, our y is going to be 0. Let's put in the values. Du dy is going to be negative 1 on 2 times 1.41, negative 1600. The b 0.05. Are we good? Minus 2 times 0. And our du with respect to the y is going to, when you punch everything here, you are going to get 28.368 per second. Are we okay? So this is the strain at 0. Therefore, my shear at the wall is going to be mu du dy, and that is going to be 1.41 multiplying 28.368. Shear is going to be 40 Newton per meter square or Pascal. Are we good? So at the wall, the shear is 40, and so this is at the wall when y is equal to 0. But at when y was equal to what? 12 mm, we saw that our shear, what was our shear value? The shear was 20.8. So as the distance increases, you can see that the shear will be what? Decreasing. So the maximum shear occurs at the what? The boundary. Do you get it? So thank you for watching this episode. And these are interesting questions. Subscribe to the channel, like, share, and let's see your comments. Follow the next episode for a deep understanding in fluid mechanics. Thank you.